Hey everybody. Today we're doing 5 problems involving some common discrete probability distributions, things like the binomial, Poisson, and hypergeometric distributions. In each case, I recommend pausing the video, trying the problem on your own, and I just want to say at the outset that each one of these problems can be done in more than one way, so if your solution doesn't exactly match up with mine, don't panic. Here's the first one. Players win prizes in a carnival game 15% of the time. What's the probability that exactly 3 tries will be needed to win a prize? So we're going to let x be the number of tries to win the first prize, and so x is going to have a geometric distribution. The probability of success on any given trial is 15%, 0.15. So the probability mass function for x is going to be pq to the x minus 1, since you need one success after you have x minus 1 failures. And so when we plug in p equals 0.15 and q equals 0.85, you can see the probability mass function there. And the support there is 1, 2, 3, etc., because x is representing the total number of tries. So to solve this problem, we just have to plug in 3. F of 3 ends up being about 0.108, so there's about 11% chance that exactly 3 tries are needed. This is a little easier to do if you're using technology. I use R, where the command is dgeom2, 0.15. R, like some other pieces of technology that you might be using, counts the number of failures before the first success rather than the total number of trials. That's why there's a 2 there rather than a 3. Problem 2. Same situation. There's a carnival game where you have a 15% chance of winning every time. This time a parent is trying to win for their child, and they have enough money to play exactly 8 times. What's the probability that they succeed at least once? Again, try this on your own before advancing. Now we could do this problem just as before, using the random variable x with a geometric distribution with parameter p equals 0.15. And if we do it that way, we need to find the probability that the first success comes in the first 8 trials. That is to say, the probability that x is less than or equal to 8. If we do that, we get 72.8%. I think there's a slightly easier way to do it, however, and that's by using the binomial distribution. Let's let y be the number of wins in 8 tries, so that has a binomial distribution. Number of successes in a sequence of trials, each where they're identical and independent with the same probability of success. We need to do the probability that we get at least one success, and that's 1 minus the probability of getting no successes. So the probability of getting no successes is 0.85 to the 8. The probability of an individual failure to the 8th power, because it has to happen 8 times. Same answer, 72.8%. In R, the command for this would be 1 minus d binom 0, 8, 0.15. Probability of 0 successes in 8 trials with a probability of success on each trial of 0.15. Problem 3. Same carnival game, 15% chance of winning on any particular try, but now the parent has 3 children and they need to win a prize for each one. What's the expected number of times they'll have to play, and what's the probability that it takes them no more than that many tries to actually win 3 times? So this time we're in a negative binomial distribution because we need a fixed number of successes, in this case r equals 3, in a sequence of Bernoulli trials. That is, random experiments with 2 possible outcomes, success and failure, that are all identical and independent of one another. The expected value is r over p, so 3 over 0.15 or 20. And the probability mass function is x minus 1 choose r minus 1 times p to the r times q to the x minus r. So we're in a situation where we have to have r successes and x minus r failures if it's taken us x tries total. So for any particular ordering of the successes and failures, the probability is p to the r times q to the x minus r. The x minus 1 choose r minus 1 is the number of ways those successes and failures can be ordered. Because the last trial has to be a success, you have to have the other r minus 1 successes in the first x minus 1 trials. The second part of this equality here is just plugging in r equals 3, p equals 0.15, and q equals 0.85 into that formula. We need to find the probability that it takes us no more than 20 trials, where 20 is the expected value. So we need to add up the values that this probability mass function takes for x equals 1, 2, 3, all the way up to 20. When we do that, we get 59.5%. So that's the probability that it takes them no more trials than that expected number of trials. Trying to do that by hand is an absolute mess, so you want to use technology for that. In R, the command is pnbinom 17, 3, 0.15. So R is 3, p equals 0.15. 17 here is representing the number of failures that happen before the third success. And so if you have 17 failures, 3 successes, that's 20 trials total. Problem 4. During a meteor shower, shooting stars occur at an average rate of 1 every 4 minutes. What's the probability of 12 occurrences in an hour? At least 12 occurrences? So this time we're in a Poisson distribution. The number of occurrences when you have random and independent occurrences happening over a unit interval of time or some other unit interval. Here we're given that we expect 1 occurrence every 4 minutes, which corresponds to 15 expected every 60 minutes. So the question is about an hour, so I need to multiply everything by 15. So we're in the Poisson distribution with parameter lambda equals 15, the expected number of occurrences. The probability mass function, lambda to the x, e to the negative lambda over x factorial, we need to plug in lambda equals 15. To compute the probability of exactly 12 occurrences, we plug in x equals 12. We get about 8.3%. And the R code for that is dPOIS 12, 0.15. By the way, I have an entire video in this probability course about doing probability calculations in R. I'll throw a link to that up top in case you're just dropping in from, say, a Google search or something. The probability of at least 12 occurrences is going to be 1 minus the probability of at most 11 occurrences. So that's 1 minus the cumulative distribution function evaluated at 11. Again, the arithmetic there is kind of rough, so I recommend using technology. In R, the command is 1 minus pPOIS 11, 0.15, and the outcome there is 81.5%. Last question. There are 25 possible questions at a technical interview, but a candidate has only had time to prepare for 15 of them. Suppose that 4 questions are going to be asked during that interview. What's the probability that the candidate will be prepared for all 4? And what's the probability that they'll be prepared for at least 3? We are now in a situation where we're doing sampling without replacement. We're taking a sample from that population of 25 possible questions. We're not having any possibility of repeats here. On each individual trial, there's 2 possibilities, either a success or a failure. Either they're prepared for the question or not. There are 15 possible successes in this set of 25, 15 questions they're prepared for, and 10 possible failures. The sample size is going to be 4. We're doing this without replacement. Again, we're in a hypergeometric distribution with those parameters. The probability mass function is given here. What's going on here is in the denominator, we're counting the total number of ways that we can pick n objects from a collection of n1 plus n2. So in this case, picking 4 from a collection of 25. The numerator is saying how many ways you can pick the x successes from the n1 that you have available, and then the rest have to be failures, so you're picking n minus x of the failures out of n2 total. The right part of that inequality is plugging in those values, n1 equals 15, n2 equals 10, and little n equals 4. The support of this random variable is just the numbers 0, 1, 2, 3, or 4, because you're only picking 4 out of there, so those are the only possibilities. We plug in 4, and then we plug in 3 to get the probabilities we need. There is a 10.8% chance that they'll be prepared for all 4. There's a 36.0% chance that they'll be prepared for exactly 3. So that means the probability that they'll be prepared for at least 3 is the sum of those two, so 46.8%.